Now, the next section is graphs of motion, right? We're going to do a few more of those things in exam and test prep, and we'll do another one or two in a little bit. But let's just get through and then do some applications of this. Okay? This section we're going to be dealing with here is called graphs of motion. Okay? Where we're going to be drawing a graph of motion. Let's just have a look at something. Can you see, remember back to our Newton's laws of motion. We had V final equals V initial plus AT. Let me just put this one. Vf squared equals, okay, Vi squared plus 2A delta x, right? We also had one that was delta x is equal to Vi t plus a half A times t squared, okay? Yeah, half AT squared, yeah, okay, right? These laws of motion that we've got here, all right? And of course, and the other one where it's acceleration is, or distance is a half Vf plus Vi over 2. But essentially, there's a factor involved in most of these laws of motion, and it comes in the word motion. Motion is what? It's movement. Movement. So let's have a look. Velocity is equal to delta x over delta t. Acceleration is delta v over delta t. Hold on. Delta t is common to it. Why? Motion means time. It's measured in time, isn't it? Motionless means we don't move for a period of time. We lie sleeping, or we just lie chilled out on a couch. We're not moving over a period of time. So now here's the key. All of our graphs of motion are going to be in terms of time. So first of all, the first graph that we're going to look at is position versus time. Okay? It's a position versus time graph. And it looks like this. All right? This is my position, this side over here, and this is the time axis here, right? Now we do this in seconds and position in meters, right? That's how we measure it. Why have I got a piece here and a piece here? Correct. Because position is going to be my displacement from the origin. Okay? Displacement from the origin. Right? These are all in the books. Okay? But let's just go through them a little carefully. Displacement here, delta x. Displacement is a what? A vector. What does that mean? Oh, it's got a direction. Positive, negative. So this means the opposite direction. All right? No, it does not mean that I'm eating myself by the tail if I'm negative. It means I'm going the opposite way. That's all it means. I'm going the opposite direction. Okay? So, let's have a look at some of these, right? You get some standard ones, right? Well, first of all, let's look at the standard ones, all right? Position versus time, okay? Well, the first one is this one, where you could have it there, or you could have a graph down there, all right? So let's fill in. This is time. This is position. So this is delta x plus. This is delta x minus over here, all right? Let's look at this line. First of all, it is a straight line. right? Straight line, and it is flat. Therefore, it has got 0 slope. Okay? It's got no slope. Well, what does that mean? Let's ask ourselves, what does it mean? It means, quite straightforward, the following, doesn't it? Okay? It means that we are flat line, we're not moving. My position, let's say this is after 10, 20, 30 seconds, I am still in the same place. The key to these graphs is to ask what is happening, right? I know a lot of people struggle with it, but the actual way is to say what happens. At 10 seconds, where am I? I'm there. At 20 seconds, I am still there. At 30 seconds, I am still there. So where am I if my origin is here? I am out here. I could be, let's say, that's 100. It means I am sitting 100 meters away from my origin. My origin is here. I am sitting over here 100 meters away. But after 20 seconds, I am still 100 meters away. After another 10, I'm still 100 meters away. Okay? I'm not moving, which means velocity is 0. I am at rest. Okay, do you see that? That's that. Now let's look at the bottom piece. Okay, let's look at the bottom one over here. Rather use red. Okay, I'm over here now. All right. Where am I? Let's say this is also given as 100 over here. Where am I? Well, I am still at 100, but I'm at minus 100. I am here. All right? So on the one, I'm 100 meters this way because I chose that way as positive. Now, the other one, I'm 100 meters behind the origin. Okay? So, the other way of looking at it is that this could be to the east and the west. Don't forget, it could also be up and down, right? I could be 100 meters up in the air or 100 meters lower than my starting point, right? Not underground, no. All right? Well, technically, I suppose I could be. But, so that's a position time graph with the two straight lines. Let's now have a look at position time graph that looks like this, shall we? Okay, just do it over here. Just get it back. Let's have a look at a position time graph that looks like that. All right? Like so. Or I'm going to do a red one, which is down here like this. All right? So let's look at the one up here. This is delta x, okay? And this is delta t over here. This could be 100 meters and 10 seconds, right? What does it mean? What did we do? We split physics up. So at time 0, where was I? I was here, right? We are here at time 0. Where are we after 10 seconds? Well, did we move? Yes. After 10 seconds, we are 100 meters away. Delta x, delta t is equal to 10 seconds. That's 100 meters, right? And I moved in a positive direction. Can you see? You just look at the graph and work out the logic on the graph, right? So we started at 0, right? After 10 seconds, where are we? We are plus 100 meters away, which means we're this way. So I'm staying here. You are 100 meters away from me after 10 seconds, right? So what did that mean? It means that during that period, how did you get there? You had to walk or run there, didn't you? Right? So what can we say? We can say the following. We can say that, first of all, let's look. This is a straight line. Okay? and it's got a positive slope, right? We have here got a delta x and a delta t, which means we've got a velocity, delta x over delta t. All right? You've got a velocity time. You moved 100 meters in 10 seconds. Right? Simple as that. Look at the red one underneath. Can you see the red line? The red line over here has got a negative slope. Okay? All that means is I moved there. I was minus 100 meters. In other words, if I sent somebody that way, I sent you the opposite way. That's all. It's just the opposite direction. Okay? So that's that. Now let's have a look at a position time graph that looks like this. Not delta t. Delta x minus, and this is our time. What if we had a graph that looked like this? Okay. Well, first of all, this is a parabola, isn't it? It's not a straight line graph, okay? This shows here a positive acceleration, okay? It's position versus time. Let's just have a look at something, shall we? Let's just go back to Newton's laws of motion. I just want to page mine back. And we said that if we look at Newton's laws of motion, let's just look at this one, okay? Delta x is equal to vi delta t plus a half a delta t squared, okay? Can you see that this here, let me just highlight it maybe in green. This is a parabolic curve, isn't it? It's a parabola, all right? So the acceleration, right, is the coefficient of the squared term. So in this case, we are moving with a positive acceleration, all right, in the positive direction, all right? Don't worry, we're going to do a few of these examples. I'm just going through the standard forms, and we'll sort of go through them one by one, okay, so that we can explain it, okay? The other thing is if the acceleration, okay, if the acceleration A is positive, right? Can you see there's the graph? If A is positive, let me just rearrange the graph like this. Delta x is equal to a half a delta, it's not a nice delta, half a delta t squared plus vi delta t, all right? The coefficient of the t squared, right, is a half a. So if this coefficient here, if the coefficient here, let me go back to blue, that's what I was in, is positive, it's a up, right, correctly up one, a smiley face, isn't it? It's a smiley face if it's pointing up like that. That means that because the coefficient of your squared term is positive, so it's pointing up. So it's a positive acceleration. What does a positive acceleration mean? I am not getting faster. I am going faster. I am accelerating. The acceleration is in the direction that I'm going. Okay? That's what that graph looks for. Then similarly, there is a graph that looks like this as well. All right? there's a graph that looks like this. All right? This is a sad face, which means I am my coefficient of t squared, sad face. Therefore, the coefficient of t squared, which is a half a, is negative. Therefore, acceleration is negative, which means I am decelerating, okay? It's slowing down, all right? Now, let's have a look at, once again, let's just go through this concept here as well, shall we? If I am moving in this direction, v is positive, right? If my acceleration is positive, okay, it means I am accelerating, doesn't it? I'm going faster because the acceleration is acting in my direction. Then I've got the next step, which is I'm going this way. V is positive, A is negative. What am I doing? I am slowing down. Okay? Right? Then we can have another one. All right? We can have this one. We can have acceleration, velocity this way, and acceleration that way. This is negative. This is negative. What does it mean? I am going opposite way. All right? In other words, backwards, if you like. This one is and accelerating. So I'm going this way and I'm accelerating that way, which means I'm going faster in that direction. The last one, logically, we could have is v is negative and acceleration is positive. What does it mean? It means I am traveling, let's say west, okay, and slowing down. Okay, I'm traveling this way, but the acceleration is this way. So I'm slowing down in this direction, probably so that I can grab a bite to eat, or then going to reverse my direction and go that way. So when you've got these, it's important to know these standard forms, okay, but to be able to logically put them together, all right? The next one is we get a velocity versus time. Velocity versus time graphs. All right? Once again, here we've got plus v minus v, and here is, I'm just going to put it as a time axis. Same as the other ones, as time axis. All right? It's an axis of time. Right? Now, well, what does it mean if I've just got a line here on the axis? Okay? Obviously, it means I'm at rest. Right? If I've got one on the axis, I am at rest. Okay? Why? Well, because my velocity isn't changing. And if the velocity isn't changing, then it means that I am standing still. Okay, plus v minus v. All right. What about this one? And obviously the concomitant one down there. Let's say that this is 5 meters per second over here. This is 5 meters per second. This, let's say, is minus 10 meters per second. It doesn't really matter. All right. What does this mean? It means my velocity, I am traveling at 5 meters per second, and I am traveling in the positive direction. Okay? It means I'm traveling with a velocity of 5 in the positive. But my velocity isn't getting bigger or smaller, which means my velocity, it's a straight line, and it's flat. Zero slope. Okay? Which means no acceleration, constant velocity. Okay? Let's think about it. My velocity at time 0 and at time 10 is the same. You see, you just go back to the curve and read it off. What's happening to me? At 0 time, I'm traveling at 5. At 10, I'm still traveling at 5, which means I'm traveling at a constant velocity. And ditto down the bottom, over here. Okay? At 20 and at 30, I am still traveling at minus 10. That means I'm traveling westwards, or traveling in that direction, in the opposite direction. Right? Now, let's have a look at the next one. Okay? Let's have a look at the next. The next one is a velocity graph that looks like this. Okay? Like that. So this is plus v minus v, and let's say we go up here, and that's 10 meters per second, and once again we've got time. Okay? And let's say we've got a red line underneath here, a different question. All right? Let's say there, that's 20 seconds, and that velocity over there is, let's say, minus 20 meters per second. All right? And let's put in a number over there. Let's say that's 5 seconds. Okay? Let's look at the black motion first. At time 0, where am I? Okay? Let's ask the question. Okay? At t equals 0, where am I? What's happening to me? Okay? Not what. What? What am I doing? Okay? Well, let's go and have a look at the graph. Well, at time 0, all I can say is at time 0, I am traveling at 0 velocity. V equals 0. Therefore, I am at rest. Okay? See what I did? I went to the graph and said, what am I doing? Let's have a look at the next one. I'm here now. After 5 seconds, I'm traveling at 10. All right? Therefore, at t equals 5, v equals 10. Okay? Therefore, what has happened? Okay? My velocity I had over here, v final equaled 10, v initial was 0. I was at rest, I'm now doing 10. Okay? I'm at 10 meters per second. I must have accelerated, because acceleration is delta v over delta t, which is going to be 10 minus 0 over 5, which is 2 meters per second squared. Okay? So, let's go back and look at the next one now, on the red one. Okay? On the red side. Well, at t0, I'm at 0, aren't I? Okay? There. And at here, at t equal 20, I am traveling at 20 meters per second, right? So, it means that at t equals 0, v was 0. At t equals 20, v equals minus 20. Therefore, acceleration is equal to, okay, minus 20 minus 0 over 20 minus 1 meter per second squared. Okay, what does that mean? It means I'm going that way. I accelerated backwards, right? That's all that it means. Okay, I accelerated backwards, right? Next one, okay, is this one. Okay, is acceleration versus time graphs, right? What do they look like? Well, if it's there, it's I'm zero acceleration. No acceleration. It's on the line. Okay? I'm not accelerating. Right? At all. So, I'm at constant velocity. Right? Zero acceleration. All right? The next one is going to be this guy here. Right? This one is going to be this guy. Okay? One at there. Plus A, minus A. Once again, time over here is 10 meters per second squared. And down at the bottom, red, minus 15 meters per second squared. Okay? What does it mean? Well, this means constant negative acceleration, which means the acceleration is in the opposite direction to positive. All right? So if I'm traveling with the velocity this way and my acceleration is this way, I am slowing it down, right? And if I'm traveling this way with an acceleration, I'm going to be going faster, aren't I? So therefore, I've got a negative acceleration. This side here is a constant positive acceleration. So as long as I'm traveling the same direction, I'm going to be going faster and faster. We don't go any further than that. We don't have variable accelerations and things like that in this. We have constant acceleration positive, constant acceleration negative, right? How do? We say, right, at 10 and at 20, we go to the graph. Pick a time. You'll see when we do one, we pick a time that is, in fact, in the sequence or the breaks that we change something. All right? So at time t, I'm traveling at 10 meters per second, accelerating at 10 meters per second squared. At time 20 seconds, I am still traveling at the same. So my acceleration hasn't changed. Read the graphs, okay? That's what actually gives these away, is reading the graphs themselves. I promise you, it works. I'm going to do an example when we get back. We're going to look at one, we're going to pull it apart, and we're going to go through it by actually looking at the graphs themselves and saying, what are we doing during this period, okay? Thanks for watching. I've gone on a little bit longer than I normally do. But as I say, the next time, before we go on to the last section, which is ticker tape timers, oh no, there's still energy as well. I'm going to do an example on the position time graphs. Thanks, and I'll see you in the next session.